We're now going to zoom way in and discover that our current carrying wire is going to produce magnetic field not only outside but inside the wire itself. And we can use Ampere's law to determine the strength of that magnetic field inside this long straight wire that is carrying a total current I out of the page here. That's all these dots, the current spread out throughout the cross section of the wire coming out of the page. It's carrying that current with a uniform current density J in this example. So this is a uniform J example. That means if you take like a little patch of surface on the cross section of that wire, a little patch of area dA, infinitesimal area, there would be an infinitesimal amount of current passing out through that little patch. So a little bit of dI passing through that little window right there coming out of the page. And that ratio, dI to dA, that's our current density. And we're saying that that's going to be constant throughout this cross section. All right, so this is the uniform J case. We begin by stating Ampere's law. And recognize that we have to choose a path for this line integral here. I'm going to choose a circular path of radius little r less than big R. Circular path here, radius little r. And decide to walk around that path or integrate that around that path counterclockwise. We're going to go in the counterclockwise direction. Here's why I'm choosing that direction. Once again, it comes down to right-hand rule. If we integrate in the counterclockwise direction around that path, then my thumb indicates that out of the page must be the direction for positive current. Since we have current flowing out of the page, we want out of the page to be the positive direction for current. Hence, counterclockwise will be our most convenient direction to integrate here. This path, by the way, this imaginary hike that we're taking is often referred to as an Amperian loop. Like with Gauss's law, we have Gaussian surfaces. Here with Ampere's law, our imaginary paths are called Amperian loops. Okay, so let's investigate this dot product at locations along that path. All of our little dS's will be little displacement vectors tangent to that path. And we can tell that there is current enclosed inside the circular area bounded by that path. There is a positive current enclosed. Therefore, we know that our integral here is non-zero. Okay, that means B can't be zero everywhere on this path, and B must actually be in the same direction as S. So B dot ds is positive, agreeing with our positive enclosed current on the right. Therefore, we're concluding that at all points on this path, we must have a B field that points in the same direction as S. And by symmetry, that B field must be the same at all points on that path. And I guess the argument I'm making here is that even on the inside of our wire, we must have looping magnetic field lines concentric with the center of the wire. So we must have B field lines looping around like that even inside the wire, circulating counterclockwise. That's the discovery that Ampere's law is forcing us into right here. Okay, so at all points on that path, which coincides with a magnetic field line inside the wire, ds will be parallel to our B field vector. So ds dot B, cosine of the angle between them is 1. So we get the magnitude of B times ds. I'll have to sum those up at all points around our wire here. By symmetry, B is a constant, so it comes out. And we just have to add up all the ds's all the way around that path. Once again, that'll be the circumference of that path. So B times 2 pi little r. Little r is the radius of that path, not big R, which is the radius of the wire as a whole. Okay, that handles the left-hand side. We just now need to consider the right-hand side, the current enclosed inside our Amperian loop. Just the current penetrating out through this membrane that is bounded by our Amperian loop. And to figure that out, we're going to make use of our current density, J, over here. All right, so J is the current per unit area passing out of the page there. And if that is indeed a constant, then we can represent this as the total current coming out through the total area. So our total current I over pi big R squared, the total cross-sectional area of the wire. So that current is spread out evenly throughout that whole cross-sectional area. If it's a uniform, then that also equals the current enclosed in any subsection of our wire divided by the area enclosed in that subsection of the wire. So that's our current enclosed divided by the area enclosed by the current enclosed in our Amperian loop divided by the area of the area bounded by our Amperian loop. So pi times little r squared, the area inside our Amperian loop. That's all showing us that our current enclosed can be expressed as the total current over pi big R squared, this, times the area of our Amperian loop, pi little r squared. Pi's cancel, and we get I times the ratio little r squared over big R squared. That's our current enclosed. That's going in here on the right-hand side of Ampere's law. So mu naught times the total current times little r squared over big R squared. Now just divide both sides by that circumference, and we have our answer. The B field, as a function of r, little r, distance from the center of the wire, has magnitude mu naught I times little r over 2 pi times big R squared. And we see it's a linear function of distance from the center of the wire. So if we make a quick graph of our B field strength as a function of distance from the center of the wire, let's say here is big R, the surface of the wire. We see we've got this linear function on the inside, B field increasing from the center outwards. So we have a weak, approaching zero magnetic field at the very center of the wire, but B field getting stronger and stronger as we approach the edge of the wire. That's this behavior. And then once we're outside the wire, for a little r greater than big R, we've previously solved to find that we get a 1 over r drop-off out there in that region.